Welcome to this video, and in this video I will be discussing the synthesis of one-port LC networks. One-port LC networks. For any transfer function to be implementable using LC networks, it must meet the following properties, or these are the properties of LC networks. Number one, the transfer function must be an odd to even or even to odd polynomial in S. It must be an odd to even or even to odd. That means if the numerator is odd ordered, the denominator is even ordered, and vice versa. Number two, the poles and zeros of the transfer function must lie on the imaginary axis, interlacing. So all the poles and zeros they must lie on the imaginary axis and they must interlace. Okay. All the poles and zeros of the transfer function must be lying on the imaginary axis and interlacing. Number three, the highest and lowest powers of the denominator and numerator polynomials must differ by unity. So the highest and lowest powers must differ by unity. And lastly, there must be either a zero or a pole at the origin. A zero or a pole at the origin. So these are the properties of a transfer function that is implementable using LC one-port networks. Let's take an example of a transfer function and investigate for those properties. Suppose you have a transfer function, an impedance transfer function Z of S given by 2 into S squared plus 1 into S squared plus 9 divided by S into S squared plus 4. The first property is on odd to even or even to odd polynomial in S. If you look at the numerator can be written as 2 into S power 4 plus 10S squared plus 9. And then the denominator is S cubed plus 4S. If we look at the numerator, the powers of S are 4, 2, and 0. So this is even. And the powers of the denominator are 3 and 1, which is odd. And therefore, this is odd to even polynomial in S, and therefore property number 1 is met. Property number 2 is that the poles and zeros must lie on the imaginary axis interlacing. If we solve for the zeros, we would say S squared plus 1 into S squared plus 9 is equals to 0. We get S squared plus 1 is 0, which will give us S to be equal to plus or minus J. Then S squared plus 9 is equals to 0, which would give us S to be equal to plus or minus J3 or 3J. If we solve for the poles are S into S squared plus 4 is equals to 0, which means S is equals to 0 is one of the poles, and S is equals to plus or minus J2 are the other poles. If we are to sketch the poles and zeros on an S-plane or a plane of real to imaginary axis, so these are the real axis and this is the imaginary axis, have 1, 2, 3, -1, -2, and -3. We have a pole at the origin at 0, so this is 1, 2, 3, -1, -2, -3. We have a pole at the origin and a pole at 2 and -2j. We have a 0 at j and -j, and a 0 at 3j and -3j. If you look at these, all the poles and zeros are on the imaginary axis and they're interlacing because we have a 0 pole, 0 pole, 0 pole, 0 in that order, and therefore property number 3 or number 2 is met. Property number 3 is on the highest powers and lowest powers of S in the denominator and numerator polynomials of our transfer function. The highest power of S in the numerator is S power 4. Then the lowest, or the highest on the denominator is S power 3. And as you can see, these ones, they differ by S power 1, which is what we are saying, they differ by unity. The lowest power of S in the denominator is S power 0 for a constant, and the highest is S. The lowest is S on the denominator, and as you can see, again, they differ by S power 1, and again, they differ by unity. And through this, then we can notice that property number 3 is met. Property number 4 is that there must be either a pole or a 0 at the origin. Notice we have a pole at 0 or a pole at the origin, and therefore the pole at the origin qualifies property number 4, and through that, all the properties of that transfer functions are met, and the transfer function is implementable using LC networks. Next, we proceed to implement the transfer function using the various canonical forms of LC network. The first one is what we call the Foster series, or sometimes what we call the fast Foster. Foster series or fast Foster. In Foster series networks, all the components are in series, and if there is any parallel combination of the components, then they must be in series with the entire network. Our network being an LC network, then you can have an inductor, a capacitor in series, and a parallel inductor capacitor which is in series with the entire network. And therefore, our network will look like that. All the components are in series. If you have a parallel combination of an inductor and capacitor, it is in series with the entire network. And this would constitute what we call a fast Foster network. Now, to implement a network in fast Foster, we use the partial fraction expansion, or we expand the transfer function in partial fraction expansion, and through that we can identify the various components and their values based on the partial parts that we get from the transfer function. If we expand and we notice that there is a term that has S, then the coefficient of that becomes our inductor, because the impedance due to an inductor is given by SL. If we have a term that has 1 over S, then the coefficient of the denominator gives us the value of the capacitance, since the inductance, or that is the impedance due to capacitor, is given by 1 over SC. Finally, when you have an inductor capacitor in parallel, the total impedance Z will be equal to SL multiplied by 1 over SC over SL plus 1 over SC, which we can write as SL over S squared LC plus 1. If we make this coefficient of S squared in the denominator to be 1, we divide by LC to get S 1 over C over S squared plus 1 over LC. And therefore, whenever we get a term that has the numerator S with a coefficient, the coefficient on the numerator will give us the value of the capacitor. And on the denominator, it's S squared plus 1 over LC. That will help us determine the value of the inductor, having calculated the capacitance from the coefficient of the numerator of that partial part. Let's proceed and implement that transfer function. Our transfer function was Z of S is given by 2 into S squared plus 1 into S squared plus 9 over S into S cubed S squared plus S squared plus 4. You notice that the order of the numerator is greater than the order of the denominator, and first we've got to divide so as to be able to write these in partial parts. If you multiply these out, you get this as 2 into S power 4 plus 10S squared plus 9 over S cubed plus 4S, which we can write as 2S power 4 plus 20S squared plus 18 divided by S cubed plus 4S, which you can write as in partial parts. First, you perform the division as S power 4 plus 20S squared plus 18. We first divide these into S cubed plus 4S. Notice we require this to be 2S to get 2S power 4 plus 8S squared, and the difference will be 12S squared plus 18. That means we can write our impedance transfer function as 2S plus 12S squared plus 18 over S cubed plus 4S, which we can write as 2S plus, then we can write these into partial parts as a constant over S plus BS over S squared plus 4, the partial parts being, the factors being S and S squared plus 4. From these, we can expand this part into the following, so that you can write the numerator as A into S squared plus 4 plus BS squared, which we compare with the numerator of this term to be 12S squared plus 18. From this, we notice our constant on the left is 4A, which will give compared to 18 or be equal to 18, from which our A will be 9 over 2. Our A plus B, being the coefficients of S squared, will be equal to 12, from which B is 12 minus A, which is minus 9 over 2, and this gives us 15 over 2. That means then our transfer function Z of S can now be written as 2S plus A over S, which is 9 over 2 over S, plus BS, which is 15 over 2S over S squared plus 4, which you can write as 2S plus then 1 over 2 over 9S plus 15 over 2S over S squared plus 4. If you look at these terms, then 2S indicates there is an inductor whose inductance is 2 Henry. 1 over 2 over 9S means there is a capacitor in series whose capacitance is 2 over 9. So I'm comparing this with SL. I compare this with 1 over SC. So the L is 2, the C is 2 over 9. Then this term, 15 over 2 plus S squared, we compare that with a parallel, that is a parallel combination of inductor capacitor whose impedance is given by S over 1 over C into S squared plus 1 over LC. That means we compare S 1 over C over S squared plus 1 over LC. We compare this with 15 over 2S over S squared plus 4, from which we notice that 1 over C will be 15 over 2, from which C will be 2 over 15. Then 1 over LC will be equal to 4. So the constant on the denominator is 4. Here it's 1 over LC, from which we notice that our L will be 1 over 4C, which is 1 over 4 times 2 over 15, and that will give us 15 over 8. From our partial parts, then we can draw our circuit as the first one is an inductor, followed by a capacitor, and then an inductor capacitor parallel network. That's our network. The value of the inductance, we noted it's 2 Henry from 2S. The capacitor is 2 over 9 farads. So you can put these as 2 Henry, 2 over 9 farads. This is 2 over 9 farads. Then the value of the capacitor here is 2 over 15 farads. And the value of the inductor is 15 over 8 Henry. And this becomes the first Foster LC network implementation of our given transfer function. The second form of implementation, or canonical form, is what we call the second Foster or the Foster parallel network. So we have the second Foster. We have the second Foster, or what we call the Foster parallel network. In the second Foster or Foster parallel network, all the components are in parallel, and if there is any series arrangement, it is in parallel with the entire network. Means you can have an inductor in parallel with a capacitor, and if there is any combination of inductor capacitor in series, it is in parallel with the entire network. So our network will be a network of that format. Inductor, capacitor, series inductor, capacitor, all of them in parallel, and that would constitute our Foster parallel or second Foster canonical form. Now you notice then that our implementation is in terms of admittance as opposed to impedance, and therefore we will implement the Foster parallel network using the admittance transfer function as opposed to the impedance transfer function. When you have the inductor in parallel, admittance due to inductor is given by 1 over SL. And therefore, if we get a value that has 1 over S with the coefficient will indicate the value of the inductor. Admittance due to capacitor is given by SC. And therefore, if we get a term with S and a coefficient, the coefficient will indicate the presence of a capacitor or the value of the capacitor in parallel. Finally, if we have an inductor capacitor in series and then in parallel with the entire network, the impedance due to the two is given by Z is SL plus 1 over SC, which you can write as S squared LC plus 1 over SC. The admittance is the reciprocal, which is SC over S squared LC plus 1. If we make the coefficient of S squared to be 1, we divide by LC, we will get S 1 over L over S squared plus 1 over LC. And from this, you notice that the numerator will be S with a coefficient, and the coefficient will help us determine the value of the inductor. And then the coefficient on the denominator will help us calculate the value of the capacitor, having calculated the value of the inductor from the numerator coefficient. And through this, then we are able to implement the second Foster LC network. Now to do this, we write the admittance transfer function in partial fraction form and obtain the component values from the various partial parts of our given transfer function. Let's extend the same to our transfer function. Our Z of S was given by 2 into S squared plus 1 into S squared plus 9 divided by S into S squared plus 4. The admittance transfer function will be equal to S into S squared plus 4 divided by 2 into S squared plus 1 into S squared plus 9, which you can write as a half S into S squared plus 4 divided by S squared plus 1 into S squared plus 9. Next, we write the partial parts. Because the denominator has S squared plus 1 and S squared plus 9, then we'll have two parts which can be written as AS over S squared plus 1 plus BS over S squared plus 9. If we put this into under common denominator, then we can write this as S squared plus 1 into S squared plus 9, then AS into S squared plus 9 plus BS into S squared plus 1. If we expand the numerator and compare with the numerator of the admittance transfer function, then we get AS cubed plus 9AS plus BS cubed plus BS is equals to a half S cubed plus 2S, from which the constant or the terms with S will give us, 9A plus B will be equal to 2. The coefficients of S squared will give us A plus B to be equal to a half. If we subtract the second one from the first, we'll get 8A to be equal to 1.5, which is 3 over 2, and our A will be 3 over 16. From the second one, you can notice that B will be a half minus A, which is minus 3 over 16, and this will give us 16, 8 minus 3, which is 5, and our B is 5 over 16. From which you can write our transfer function. We can write our transfer function Y of S to be AS, which is 3 over 16S over S squared plus 1 plus 5 over 16S over S squared plus 9. Then we take each of the parts and compare with the transfer function of, or the admittance function of a series LC network, which we derived as S into 1 over L over S squared plus 1 over LC. So we compare those and we can say 3 over 16S over S squared plus 1 is being compared to S 1 over L. We compare this with S into 1 over L. This is L, and then S squared plus 1 over LC, from which we notice 1 over L will be equal to 3 over 16, and L will be equal to 16 over 3. Then we can write 1 over LC is 1, from which C will be 1 over L, and this will be 3 over 16 farad. Of course, this in Henry. Next, we compare 5 over 16S over S squared plus 9. We compare this to S, 1 over L, and then S squared plus 1 over LC, from which you can say 1 over L is equals to 5 over 16, the numerator parts, and L will be 16 over 5 Henry. Then 1 over LC is equal to 9, the coefficient or the constant in the denominator, from which C will be 1 over 9L, which is 1 over 9 times 16 over 5, and this will give us 5 over 9 times 16, which is 144 farads. From this, then we can draw our network. We can draw our network as a network that has two series inductor capacitor network, but they're in parallel. This is our Foster parallel network. The value of the inductance in the first one is 16 over 3 Henry. The value of the capacitance is 3 over 16 farad. Then this is 16 over 5 Henry, and this is 5 over 144 farads. And this will be the implementation of the circuit one-port network for the admittance transfer function, or the Foster parallel implementation of our transfer function. Number 3 is what we call the Kawa network, the Kawa canonical form of the LC network. For us to be able to write the Kawa or to be able to implement the Kawa canonical form, we need first to write the transfer function in descending orders of S, and then use the continuous fraction expansion to obtain the component parameters. Now, a Kawa network is basically a ladder network where we have series parallel combination of the network alternating each other. So you can have an inductor in series, a capacitor in parallel, inductor in series, capacitor in parallel, like that. And this forms a Kawa network, or what we would call a ladder network. Now, when we write the transfer function in descending powers of S, then we've got to compute the continuous fraction expansion of that, from which we can be able to implement the network by determining the component values. Let's proceed to implement our transfer function using Kawa 1. Our Z of S was given by 2S power 4 plus 20S squared plus 18 divided by S power 3 plus 4S. We're supposed to write this in descending orders of S for both the numerator and the denominator. And as you can see, it is already in descending powers of S. Next, we expand these in continuous fraction expansion. So we take S power 4 plus 20S squared plus 18. We divide these into S cubed plus 4S. So to get 2S power 4 from S cubed, we need 2S. And this gives us 2S power 4 plus 8S squared. The difference gives us 12S squared plus 18. Next, we divide these into S cubed plus 4S. So the term that we have here we divide into the remainder. To get s cubed from 12s squared, we need 1 over 12s. We need 1 over 12s, from which we can get s cubed plus 18 over 12 is the same as 3 over 2s. And the difference will give us 5 over 2s, which we divide into 12s squared plus 18. To get 12s squared from 5 over 2s, then we multiply this by 24 over 5, multiplied by 5 over 2. So this gives us 12. So we need to multiply this by 24 over 5s. So this one is going to give us 12s squared. The difference is 18. We divide this into 5 over 2s. To get 5 over 2s from 18, then we need to multiply 5 over 2 by 36 over 5 to get, we want to get 5 over 2, sorry. We want to get 5 over 2 from 18, so I need 18. I multiply by 5 over 36 to get 5 over 2. So this term here will be 5 over 36s, and that gives us 5 over 2, 5 over 2s, and the difference, as you can see, will be 0. Through that, then we're able to write the partial parts. From this, we can draw our network as follows. The first term will give us an inductor in series whose inductance is 2 Henry. Notice we compare this with SL, and the inductance will be 2 Henry. Next, we have a capacitor in parallel. Sorry, this is a capacitor in parallel. If you compare this with SC, you notice that the value of the capacitance is 1 over 12, and therefore we have 1 over 12 farads. Next, we have an inductor. This is 24 over 5s, which we compare with SL, from which L is 24 over 5, and therefore this is 24 over 5 Henry. And lastly, we have a capacitor, and the value of the capacitance, because we have 5 over 36s, we are comparing this with SC, the capacitance is 5 over 36 farads. And this becomes the Kawa 1 form, or the canonical form of the implementation of the LC network. Lastly, we have what we call the Kawa 2 network. In Kawa 2 network, we write the transfer function in ascending powers of S. We write the transfer function in ascending powers of S, and we use continuous fraction expansion to decompose our given transfer function. At the end of the day, we can have a network that has a capacitor in series, an inductor in parallel, capacitor in series, inductor in parallel, in that order. And that would give us the the Kawa 2 canonical form of the LC network. So it's capacitor in series, inductor in parallel, in that order. We need to write our transfer function, which was given by Z of S to be 2S power 4 plus 20S squared plus 18 divided by S cubed plus 4s in ascending powers of s, which you can write as in ascending powers of s. This can be written as 18 plus 20s squared plus 2s power 4. We divide this into 4s plus s cubed. Then we write this in continuous fraction expansion as 18 plus 20s squared plus 2s power 4. We divide this into 4s plus s cubed. We want 18 from 4s. To get 18 from 4s, we need to multiply this by 9 over 2s. We need to multiply this by 9 over 2s. So 9 over 2s multiplied by 4s will give us 18. This will give us 18 plus 9 over 2s squared. And the difference will be 40 minus 9, which is 31 over 2s squared plus 2s power 4. And we divide this into 4s plus s cubed. This is s cubed. We want to get 4s from 31 over 2s squared. So if we take 31 over 2s squared, you multiply this by 8 over, or you multiply this by 8 over 31s, multiply this by 8 over 31s, then we'll get 4s. So that one and that one would cancel out, then this would give us 4, this would cancel out 4. We need to multiply this by 8 over 31s, and this will give us 4s plus, then this will give us 16 over 31s cubed. The difference will be 15 over 31s cubed, which we divide into 31 over 2s squared plus 2s power 4. So I want to get 31 over 2 from 15 over 31. So I take 15 over 31. I multiply this by 961 over 30, so that this will give us 2, and this will give us 31. And therefore, the term here is 961 over 30s, which I should have written here, but we can just notice, we can just note we've written it here, which will give us 31 over 2s squared. The difference is 2s power 4, which we divide into 15 over 2s cubed. The s is on the denominator. It's good to note that the s is on the denominator. So this is 31s. Finally, we need 15 over 2 from 2, which means we can multiply the term. I need 15 over 2. It's 15 over 31, sorry, it's 15 over 31. This term is 31. I need 15 over 31 from 2. That means I multiply this with 62 over 31. I need 15 over 31. I need to multiply 2 times that 15 over 62, so that this will give us that 15 over 1. And therefore, the term here is 15 over 62s. So the s again is on the denominator, so that the s and s power 4 gives us s cubed. And our term is 15 over 62s. Next, we can write our circuit as follows. Our first term is a capacitor in series. So we are comparing 9/2s. We are comparing 9/2s with 1/SC. We are comparing this with 1/SC. And we notice that C will be 2/9. So this capacitor is 2/9 farads. Then we have an inductor in parallel. We have 81/31s. Admittance due to an inductor is 1/SL. So 8/31s is the same as 1/1/8. And therefore, the inductance will be 31/8 Henry. Next, we have a capacitor for this term. And the capacitance will follow the same pattern, will be 31/961 farads. And finally, we have an inductor whose inductance is the reciprocal of 15/62, which is 16/15 Henry. And this is the Kawa 2 implementation of our transfer function. And that gives us the 4 canonical forms of implementation of the one-port LC networks: the Foster series, the Foster parallel, Kawa 1, and Kawa 2 canonical forms. Thank you for watching my video.